And we're recording. Right, lovely. Thank you very much for joining us in person and online. This is session 5 of our MOGE discussion series, where we review chapters of the Manual of Geotechnical Engineering, inviting the authors to speak on the chapters and the interesting things that they've written or what they couldn't. Our speakers today are Fraser Chamely of Arup, Joe Strange of CGL, and Chris Russell of RGI. And they've chosen to sit in the audience, which is why you can't see them online. But they will come and stand here for their presentations, I promise. Don't think we have any housekeeping to do. I think the only thing to start with is Slido. Any questions? There'll be a Q&A at the end, and you can ask questions at any time. Submit questions anytime via the Slido if you want to scan the QR code now so that you can drop questions in as you want. The link will remain on the slides throughout, so you can join that way as well. Please do ask questions, and there's a poll to start with, which asks the question whether what level of experience you have with environmental engineering, geotechnical, or whether you dabble in both worlds. And we will see the results at the end. And lovely. Cool. So our first speaker is Fraser Chamely, Senior Consultant at Arup. Fraser studied Applied Geology at Exeter, followed by an MSc in Environmental Pollution at Reading. Upon graduating, he joined CGL, where he rapidly progressed to Chartered Senior Geo-Environmental Engineer. And he took me out to my first site work, which was very nice of him. Gave me an introduction to chalk logging. After 6 years at CGL, he joined the Arup Land Quality and Contaminated Land team, where he's been for 3 years providing a variety of geo-environmental consultancy services with a focus on contamination risk assessment and due diligence advisory. And Fraser, I'll hand it over to you. Thank you very much.
Thank you very much, Charles. No fun. Still, as they always want those in these things. So, you are in Arup's office, quite a large consultancy firm, 18,000 people these days, 94 offices, 36 other countries, 34 now. Doing a wide range of services, various consultancy, and primarily in the architectural realms. But so on to the chapter, so Geo-Environmental investigation. So the MOGE book is obviously focused primarily on geotechnical engineering. It's one of the few chapters which is really relevant to the sort of geo-environmental discipline as a whole. It is a complicated area, so it's not something you can really cover off in a single chapter. This is really just a whistle-stop tour. You really need, if you are going to be doing geo-environmental sort of contamination work, it is sort of something you would want to look at, getting specialist advice on most of the time. So a few key things in the book really was around how to pick what you're going to investigate. So where you're taking your samples, what you're sampling, and what to actually test it for. So I tried to go into a little bit more detail around a few of these topics. So split it. So where to investigate, where to sample, what to test, and a little bit more discussion around a couple of the key points around sampling containers, lab variants, and then a little project example at the end to bring together some of the threads. So for the main part, where to investigate, the key bit you're going to be looking at is what are you actually going to be testing. There are two main forms of investigation sort of types. So you targeted investigation, where you're picking individual points. This is primarily going to be based around your conceptual site model, your desk study or previous investigation, where you've got known areas or suspected areas of contamination that you might be looking at. In this particular project example, we have some tank bases, some former ones that were there. Now they're just these concrete pads that were targeted to look at whether there was contamination present around them. You could also be looking at particular stratum. If you knew there were records of a layer of, say, made ground that had been placed with asbestos, say, you could be targeting that. Then the other option, non-targeted testing, so systemic systematic, sorry to say, where you're looking at doing a sort of a grid pattern or some other way of designing a methodology to investigate the site as a whole. So these wouldn't be looking at targeted positions as such. The idea is to give general coverage of the site to try and find unexpected contamination, or to do things like looking at statistical analysis upon it. And the idea with that is to bring out the bias we naturally have. In this particular instance, we have a sort of a simple 20-meter grid pattern where points are put in individually. And the key thing here is if we had followed this particular pattern on this example site, we'd have missed those 2 tank foundations. They wouldn't have been in the pad in the grid. And then we have quite large spaces elsewhere still. So even with a 20-meter grid, that's a lot of positions, but we are only still investigating a very small area of the site. So you cannot rely on this to find any of the point sources, which is why it's really important. You've done your depth study, you've developed a conceptual model, and you are targeting those areas where there's a higher risk. This should really be relied upon to look at the site as a whole. You're not targeting particular features. The other thing to note in this particular instance, in the top left corner, the second one in, where the 3 lines are, that's HV cable in this instance. So we can't actually put that borehole where it's shown on this plan. We would have to move it. So we've naturally just instantly lost our unbiased nature that was derived from the scheme. End of the day, so most sites are going to be a combination of the 2. So this is the actual GI plan that was put forward. So targeted investigation around the tank bases, followed by a systemic sort of pattern across it. In this instance, we've gone with a herringbone pattern, so they are slightly staggered. That improves the statistical likelihood of finding a particular contaminant source of certain sizes. There are various guidances around how to set out what spacing you would want for it, and they're primarily based around the area that you're expecting of the contamination area that you're looking for, so a 10-meter sort of zone of contamination or a 20-meter zone, and then looking at what percentage chance you want them. One key thing to note with this is we do still have some points that need to get moved around even with our pattern, so you would have to use some sort of engineering judgment. And then the other factor that always comes with these is access. So the grey areas in the north are former buildings. At the time we did our ground investigation, the buildings had gone, so we were able to do them. But obviously, you might struggle to get your client to allow you to drill a hole through their important building. And talking of clients, the last thing saying this is it's very easy to design a GI without really considering what the client wants. If you were trying to aim to find a 5-meter hotspot, you could easily end up on a site list with 100, 200 positions, and no client is going to pay you to do that without a very good reason, which if you're just trying to find and prove there isn't anything there, it's probably not going to meet that box for them. So we've decided where we're going to drill, and now you have to work out how deep you're going to drill. Again, this really needs to be based around understanding the CSM and what pathways you're looking at. What are you trying to investigate? There are too many different options to really go through it in this one particular sort of topic. So I've just pulled out a couple to give it a flavour of it. On the left, we have an existing area of sort of landscaping. So if we're looking at, say, a park, and we want to make sure that the soils there aren't posing a risk to current site users, we would be looking at working out what are the main exposure pathways. So we're primarily looking at direct exposure. What are the people going to be touching? What are they going to be inhaling? What are they ingesting if they're exposed to that soil? So we would be focusing on that upper surface of the soil. Typically, we would say half a meter if you're not going to be digging holes within it. But you could potentially reduce it down further, particularly if you've got areas of landscaping that are more densely vegetated. So by reducing that level of depth, you could maybe get a lot more shallow positions in rather than a few deeper positions, and give much better coverage to your site than if you were to just go with it a default, say, 5-meter window samples across that whole area. In our middle example, we've got sort of a reduced level dig. So if we are looking at a site where we're going to cut down all of that material, there's sort of 2 key environmental aspects we'd be looking at. Firstly, you need to know what's in that material you're going to remove. So we wanted to do a sort of a waste classification, as we call it, to work out what landfill, or well, hopefully not a landfill, that material can go to when it's excavated. So you'd want to be making sure that you're testing to the full depth of it. And then we effectively go back to our original sort of the left example, where when we're actually doing assessment of what risks there might be to the construction workers, we then need to consider what the new formation level is, and that's going to be at that deeper depth. So we need to make sure our sampling covers through the full depth of what we're looking for. And if that changes, we might have to actually come back and look at it again. The other thing to look at here is we don't have vapor risk in these first 2, so we don't have to consider it. But in our third model, residential, we now have intrusive buildings. So we're now looking at new pathways. And the particular one here is, so that we have an internal space, ground gases, volatile vapors can accumulate within those, whereas in our other two, we don't have a structure, so the natural ventilation usually means they're not a major concern. So for that one, we've got around the building, you could probably do shallow investigation if you want to, but within the building, you've suddenly got a deeper area that you have to look at to make sure you're covering all assessment. And that's why it's so important, so that you look at how much you need to do beforehand before you get to site. And so it's really important that CSM, the conceptual site model, is thoroughly developed. And even once we've decided how deep we're going to take them, you then get onto the stage of deciding what you're actually going to sample. So we've just a couple of examples here of some on-site works. Fairly typical London geology on the left, where we've got a 5-meter window sample, dynamic sampler cores. So we've got about 0.7 meters of made ground, quite a lot of brick, a bit of clay sort of material. We have about 300 mil of alluvium, followed by a couple of meters of a sort of silty sand, sort of superficial deposit. I believe, off the top of my head, this one was a Langley silt. And then we're on to London clay, 2 meters of that. On the right, we've got a tar pit where we have two quite distinct layers of made ground, the dark black sort of one at the top, and then a ½ meter or so of some more sort of brick fill, sort of more like 6F2, over a couple of meters again of sort of alluvial clay. A simple pattern you often see, you end up with two people look at, say, take samples every ½ meter. That may work on some sites. In this instance, for our window sample, that would probably be an okay one for this example. We have sampled our made ground. We don't have very much of it, so a single sample is probably okay. It's fairly representative of that whole mass, where other than the brick, it looks pretty continuous. We do have a sample of our alluvium, which is probably all right. And then we have 8 samples of our superficial sort of clays underneath, which for an environmental assessment is probably way too many. But unless we are really considering what the risk from that material is, if they're clean, unnatural sort of soil, we don't need that many samples. We wouldn't want to test it. We'd be wasting our clients' money if we did all that testing on it. For our trial pit, though, more importantly, you can see here, if we just do our ½ meter interval for testing, we've missed that top layer entirely. We have a single sample of the underlying material. But when it comes to assessment, when we actually have to look at what are the risks from that top made ground, we can say it's visibly different, it's a different material, we wouldn't have a sample from it. So it's taking a step back and looking at a bit more of a nuanced approach. For the window sample, we still have the same sort of testing in the upper 2 meters, but we've reduced down the number of samples from our down to 3 in our deeper sort of natural soils below that 3 meter mark. We've also staggered them, so as well as just looking at individual position, you'd want to look at the other positions nearby and try and get a decent range of samples over the various depths. So we're not just sampling again at every sample 0.5 meters. So you've got 0.3, 0.7, 0.8, and vary them across them to try and give that much more broad coverage. For the trial pit, though, on the other hand, depending on how many positions you might have in this area, in this one, we only had a few trial pits in this area, so we took 2 samples from that upper made ground, so we'd have a little bit of variance within it, and then 2 samples of the deep made ground. So we've gone up to 4 samples with that to give much more information for what we're actually really interested in looking at, that upper part where we would expect there to be contamination. In the underlying clay, we've still got a couple just to provide that coverage, see if there's anything spread around. Fortunately, not all things are quite so easy. In this particular example, we actually had about 7 meters of made ground, including 2 layers of concrete. About 3 meters and down at the 6 odd meters and again a deeper layer. So quite complicated. And then the infill material in the middle, part of it is a sandy sort of clay sort of fill, but other parts you can sort of see in the very middle, we've got metal, we've got wood. We haven't got great recovery, so we can't take our samples in this really, and this is a challenge that you won't always be able to apply that rule of thumb. In this instance, then we have to go back, we have to really look at it and work out where exactly do we want to take our samples. One of the more interesting things on this one as well is that the base of that concrete was actually sort of impregnated with an oily sort of residue, but there was just no way that we could take a sample of it. It would just be a lump of concrete that wouldn't be an appropriate soil medium really. The other thing to look at is gravels, basically. Coarse fractions are very hard to sample for geo-environmental works. For a sort of geotechnical test, you'd want to take a very nice representative sort of bulk of it with all those sort of size ranges present accounted for, and you may have to take several bulk bags for it. For the environmental aspect, primarily your contamination is going to be focused within your fine fraction. Those lumps of concrete and brick, unlikely to really represent a risk when we're looking at, say, our inhalation, ingestion, dermal exposure. They're just not the main source. If we had something like a sort of a clinkery material, we may have to change that approach, but your usual rule of thumb is that they're not really going to be representative or required for contamination assessment. So if we're looking at, say, an environmental assessment where we're looking at what risks are posed by this material, we really have to think about what are we going to sample. we could take a representative sample if we can even fit the brick inside our sampling jars, which are often quite small. But when the lab get it, they're going to grind it down. They're going to take a tiny subsample of it. And so effectively, we'll have diluted down our fine fractions. So we have to work out, are we taking representative risk factor where we're actually really looking at what are the risks from that fine material? Or are we going to take something more representative of the whole? So if we're doing an environmental test, we may want to just sample out and sort of effectively subdivide it and do a bit of a sample of just that fine material. But if we're on the other hand, if you're looking at, say, like a waste assessment, the actual total mass of that contaminant is far more important. And you don't want to do that because then you're going to be finding out that you've overestimated the amount of contaminant within that material for the terms of its waste classifications. But simply, at the end of the day, there's no way to environmentally test something like that without having effectively a bit of bias in how you're going to do it. Key part of that would just be to record it, so you make sure you have the records to understand when you look at your lab results back, to understand what was done to it and how it was manipulated, change of custody and all that. I think to look at here is a couple of nice examples of a sort of point contamination. On the left, we have a very viscous sort of tarry residue on a bit of concrete. On the right, we have our classic ACM, asbestos-containing material. So how would we actually sample this? You could take these as part of your general sampling if you're lucky enough that they fall at your sample depths, but that may not be the best approach. You really need to think about what are you actually going to be using the information for. You could take a sample, just that tire material, to have a really good detailed sample that you can send off NASA's and hopefully understand what it is, where it's come from, and the risk it poses as a whole. But on the other hand, that would vastly overestimate the contaminant concentrations as a material, as a mass. So again, if you're looking at a waste or just risk as a more sort of generally, you may want to mix it in with it. For the ACM, similar approach, you could take that as an individual sort of bulk sample, send it off, and the lab will give you an actual test result for that asbestos sort of fragment, how much asbestos is in it. You could send it off within that soil matrix, and they would do similar. But if you take it out as a sort of a bulk sample on its own and then send the soil off, if we somehow end up with the soil sample coming back with no asbestos detected, you'd need to remember that you've taken it out. You've already subsampled it out there, and it would be quite inappropriate to then say that the soils had no asbestos simply because your bulk sample has already removed it. That may not happen. You would often find trace amounts of fibers in it, but it does happen. So again, it's where the idea that if you have taken these samples, you really need to remember what they are when it comes to scheduling. The other thing on scheduling is I've seen far too many times where we take a sample of this and seeing that asbestos sample get tested for things like TPH because the engineer has forgotten what that sample was and what was tested for. And you don't really want to be the one where the lab comes back and tells you that they cannot undertake that testing because it's just not appropriate. The other thing to look at is sample quality. So the samples need to be representative of the materials as a whole. So really, when you're excavating, you want to segregate each type of main ground so you can take a representative sample of that material. In this instance, they've all been mixed up. So maybe if the engineer, while it's being excavated, keeps a very good track, he might be able to remember which materials come from which depth. But if there was any real contamination there, there's a really good likelihood that it's all been cross-contaminated, particularly say something like asbestos, where very low concentrations will just move around between that material. And the other thing is holding time, and material quality. So particularly volatile, they get volatilized out of a sample very quickly in hot weather. And even for other things, we really want to have it in as close to the in situ parameters as possible. So you should be taking them as quickly as you can to maintain it and then getting them into a cool box and off the lab as quickly as possible. In this instance, for this particular one, this has been left in quite hot sun for several hours. You can see it's already, the outside is completely dried out. It would not give very good representative samples. If you were to take these and compare it to fresh samples, it could be orders of magnitude difference in the concentrations that the lab would report. And there'd be no way of knowing other than the engineer's sort of knowledge that what the difference was between those samples. If you put them in the cool box, the lab will no longer be able to tell you. You might be able to work it out from the moisture content, and that sort of forensic testing does happen and can catch people out where effectively this could be the difference between these material passing an assessment for saying it's, or failing the assessment for how much hydrocarbons are being recorded. After all that, you actually have to decide what you're going to test for. There is no one shot for it all. Most companies will have a standard suite or set of suites, but those are guides. And most of them will cover off your general contaminants, but it's vital that they are reviewed against what you're expecting the contaminants concerned to be for each site and making sure that you pick it up. It can be a real problem where a site is, if you find in your desk study a particular contaminant concern, you don't test for it, your company is liable for that risk when it comes to it, and the client will not be happy. There are a variety of contaminants. This particular example is just out of our Arup sort of spec, which follows the ICE standard. So we pick out a few. We won't test for everything. You cannot test every sample for everything. You spend thousands of pounds. It would just be inappropriate. You have to pick and choose. Key examples in here like PCBs, sort of the middle one, E6. These are particularly commonly associated with transformers, substations. If you have them, you probably need to test them. Regulators know about it, but you wouldn't want to test it for other things. There are some other examples where that would be the case. Also, emerging contaminants, PFAS is a sort of a buzzword these days, and it has to be. We are now finding it everywhere we look, particularly water samples. It's quite key to make sure you're testing for it. So again, comes back to the CSM is king for so much in the environmental testing. Sample containers. Another common mistake is you'll end up with deviated samples if you put inappropriate ones in. Every lab has slightly different containers, and the key part is that you need to know what containers go for which testing. So you need to plan that before you get to site, before you've started putting your samples in those containers to make sure you've got the appropriate mediums for what you want to be testing. You obviously need to be reactive, that if you find things that you add to testing, you may need to alter that part. But again, it comes back to that planning part. Here we just have some very classic sort of standard examples. A small glass jar for VOCs, as it's labeled, a slightly larger glass jar that will be for the more sensitive organics, and then a large tub, which is usually used for insensitive testing and leachates. Water and gas, very different samples. You would need to check with those. They are even more different by each lab as well. Something else talking about labs is every lab has slightly different methodologies, slightly different limits of detection, and slightly different accuracies. Here we have an example of some recent work we did where we had some issues with fairly random concentrations of pHs appearing in a certain set of water. So we took 6 samples from the same well, same time, sent off to 3 different labs. So each lab has 2 duplicates effectively. And we didn't test everything, all the samples for everything, but you can really see, say for the benzoantacene and for some of the TPH fractions, it's quite a difference, double, triple the concentrations being recorded, non-detect versus detect. And some of the labs aren't consistent with it. This may be because when you are sending a sample to a lab, they are only actually running an analysis on, say, 10 grams of soil or even less water. So if you send them a large tub, 500 grams, they could take 20 samples of that and get 20 different results, let alone accounting for the accuracy of the lab itself for their analysis. So when you're taking your samples, you need to really think about how many do you need to get an accurate number that you can rely upon. In this instance, I mean, they're very low concentrations still, but it was a really interesting experience working with this. We hadn't appreciated how much variance there would be between labs on the exact same water sample, taking the exact same time, exact same methods. So applying this to a site, it's a particular one that I'm currently working on. So it's a small commercial site, little analytical lab on it, which is labeled. It has a relatively modern fuel tank, so it has quite a nice bund built around it, decent modern records, so you wouldn't expect it to be a real source. It is built in an area that has a wide sort of legacy of contamination and some industrial units. But when we were approaching the site, we really didn't expect to find anything. It looked like a fairly standard one that we're just going to go through the process, get through planning, shouldn't really have found anything. I think key thing here was the site is heavily vegetated and it was on quite a slope, so we did have limitations on where we could put positions. This is the scope of works that we actually undertook. It is a combined geotechnical, geo-environmental testing, so they're not all for that purpose. A lot of the trial pits are actually to look at foundations, but the main ones around the wider site were focused around effectively looking at where we might find sort of general coverage for contamination. We didn't have any point sources that we were looking at to investigate. So we have a combination of deep boreholes with installs, CP ones, to look at the water, slightly shallower window samples to sort of 5 meters and a few trial pits to give a bit more coverage in the sort of the south area. And very surprisingly, we were quite surprised, I'd say. So in the northwest, we have cyanide, 300 milligrams per kilogram, very high concentrations for a soil with no real reason. And more interestingly, we found it in the gravels, the natural soil. So we would expect to find that in the ground, but the overlying materials have actually clean. So we went back and did a bunch more testing of it, which we'll talk about in a bit. In the south, we have some hydrocarbons around the tank, so there's a leaking fuel line from it. Not really a big issue, but 3,000 milligrams per kilogram, just immediately adjacent to it. And then the big issue for the site was the region, sort of quite widespread groundwater contamination, toluene, chlorinated solvents, very high concentrations of 12 milligrams per litre, which is substantially above the limits that you're allowed for it. And we had no known source really, so we had to go back. And then we looked again at some of the planning reports available for the adjacent sites and discovered one of them had been a yard that had some remedial works done in like the 90s for similar contaminants, as it turned out, and had supposedly been passed. But looking again, we then designed a second phase of investigation So we did more positions on the east, and we discovered, yeah, we have a plume of groundwater contamination coming across from our site to the east for a supposedly remediated clean site that is spread all the way through ours. So even though we had a cleanish site, we still did investigation. We found something. We have the groundwater contamination from the adjacent site, but we do have our cyanide that we have no known source from. And it was so easy. If you took that sample half a meter to the left, we probably wouldn't have found it. We did in those trial pits around it. There was no detected cyanide. But having done more water in the area, we've actually now got quite high concentrations in our groundwater around the area. So that's going to be progressed forward as a sort of remediation just for that particular reason. And yeah, and we found some caveat that we're also trying to work through as to where that may have come from. Over to you, Jay.
Thank you very much, Fraser. So our next speaker will also be speaking about the geo-environmental aspects. Jo studied civil and environmental engineering at Liverpool, and started her career at Michelle, working variously in geotech, structures, and grain handling.
Yeah,
apparently.
Yeah, silos and conveyor belts.
Silos and conveyor belts. It's basically sand. Staying with that team for 8 years. Then Jo moved to Frank Graham, now WSP, working in their geo-environmental and geotechnical departments. Worked there for 5 years, moving on to Babtai Group, now Jacobs, and was there for 2 years. And then Jo moved to CGL, where she is currently. And she's been a major force in the Geo-Environmental team for over 20 years, and now leads the Enviro team as technical director. Thank you very much.
Thank you, Charles. I'm glad at my old age and wrinkliness I managed to get down the stairs without falling, so that's a good start. Yes, I've worked for CGL now for 22 years. Small company, complete opposite to where Fraser's ended up with the multinational. We are small but UK based, and we are recruiting. If we've got any grads and any new engineers that are looking to join in geo-environmental or geotechnical teams, where we focus on training and building people to be the best they can be, give me a call, and I'll try and work this now. So following on from the case study bit, and I apologise if there's a little bit of overlap between what Fraser's been talking about, because he's been talking about the sampling processes, and I'm looking more at the testing side. But this was an example that we had fairly recently where we were testing a site for E. coli. The client was a housing developer. They'd found E. coli in the water well belonging to a house next to their development who had their own well in the garden. For some reason, E. coli appeared. But we were trying to test it. Testing for bacteria is challenging. Has a very short sample life. Once you take that sample, it will degrade very quickly. So you have a 24-hour window from the sampling to the testing. And even the sampling process is quite interesting. It's not often that we have to go to site. We have to wash our hands, turn the tap on, leave the tap running for 2 minutes, disinfect the tap. The sampling methodology says, then please, you need to clean up the tap by putting it under a naked flame for a minute. Let's say no, we didn't do that. We used alcohol wipes instead, but that was an option. It did prefer us to actually put a naked flame on, unless of course it was a plastic tap. You then run the tap again for another 2 minutes. You then have a jar that is what's the word? It's basically all cleaned up. So you really don't want to contaminate the jar that you're going to use. So you then have to take your sample, making sure you don't splash things into it. Grab that, and then you have a 24-hour time limit to get that sample to the lab and tested before it deviates. So you have to record the time of sampling. And I would say that not many people would do that with soils. Maybe Fraser, you would agree with me. You would record the date, but you're not going to say I took that sample at 9 o'clock in the morning or 20 past 8 or 4 o'clock. For this type of sampling, you do need to know. And what were the issues? You need to know the why and the what. what we found was that although we took the samples on time and we delivered them to the lab, the message had not got through from the lab, from us to the lab. We'd sent the message, they hadn't read it, saying this needs to be in the machine, on the instrument, within 24 hours and tested. So they sent us back results saying this is deviating because we tested it at 10 o'clock in the morning and you took the sample at 9 o'clock. Fail. We told them, so big arguments between the labs. Does it really matter? We were fortunate in this case because we still had a positive E. coli result. And that was what we were looking for. Was it positive or not, or negative? If we had got a negative result from that test, we would have had to have gone back and got more samples because we could have had a false negative. So in the scheme of what we've been talking about is knowing the purpose of your sample, knowing the purpose of your testing. So that's the why and the what. Because if you don't know that, then you can't control what you're sampling for, and you can't control what you schedule it for, and you can't control how you get the results. So being aware of those things is really quite critical in how you deliver your investigation and how you deliver your sampling and your testing. So if we go back to moving forwards to the primary subject that I was going to talk about is the chemical testing. Why do we do it? Why do we do this testing? There's numerous reasons. Quite often, those of you that do work in development and contaminated land, it will be for some sort of risk assessment, whether it's human health, whether it's controlled waters, whether it's vapors. That's what we're looking for, that risk assessment that builds into our CSM. We're also looking at waste classification, and your samples may be doubling up on that, but just be careful that you're testing the right thing for both purposes. You might be looking at occupational health. You know, how much dust is in the air when somebody's working on that site? Is it an issue? Fate transport modelling and assessment. That's possibly a second level of assessment where you realise you've got a problem. And as Fraser was describing in his case study, you dig deeper and you start to look, well, what is happening here? We've found a hotspot of something. Where does it go? How does it get there? What are the details of that ground model? How does it move through the ground? How does it move through the groundwater? Have we got the right parameters to model that? And then potentially remediation verification. So you've done the works. How do you prove it? How do you prove to the regulators that you've done what you said you were going to do? Are they going to take your word for it? What is the evidence you can put in front of them? So what are we actually going to test for? Our contaminants of concern. And this is a little bit of overlap, but I'm going to repeat it because it bears repeating. Having a really good, robust desk study, having a really good conceptual site model, and I would always say, draw it. Don't try and describe it in words. Put it on a picture. Doesn't matter, just a little sketch. Draw your little men, and think, right, this is what our ground model looks like. This is what our contamination is likely to be. How does that move through that model? And if you don't know any of the answers on that, that's how you target your sampling and your testing. How do we build the conceptual site model to the point where we know what we've got and we know what we haven't got? And how do we fill the gaps? Fraser's talked about some suites. You know, are we looking at specific contaminants? So maybe you walk onto a site and it was a chemical works making a certain type of product. Then you know what their inventory is, you know what they've stored, you can test for those things. Or are you just looking widespread? We don't know really, it's made ground, what could be there? But you can also look at the site history. Say there was a gasworks half a mile down the road and you've got an infilled hole. Are we likely to get gasworks waste in that hole? Depending on when it was infilled, I would suggest possibly if the gasworks was operational in the 1950s, round about that time, a new hole was infilled in the 1950s, somebody might well have shoved their stuff in that hole. So you can be prepared and look for what you need. And what samples do we need to take? Are we just looking at soil? You know, is water an issue? Do we have an aquifer? Do we have controlled waters? If we have waters at depth, do we have something in the soil that could impact the water? Do we need to know its leachability, its mobility through the model? Dust and particulates. I would say it's rarely done, but it's becoming more and more a requirement of environmental management plans for construction. So your CEMP will have in it how to monitor dust. So how are you going to sample that? How are you going to test it? Asbestos. I can remember not that long ago, asbestos testing was rare and the labs really struggled with it. Now I would say all made ground samples are probably tested for asbestos, and a lot of them find asbestos. Fugitive fibres, not necessarily the big lumps that we've seen, but those fugitive fibres we need to know about. It affects not only your risk assessment, but your waste classification. And vapours, where are they coming from? From the soil, from the groundwater? Where's your source? How does it move? These are all the questions that we're asking ourselves when we're thinking about what do we sample, what do we test? So how do we select the laboratory? Do you need to know whether that sample is whether that test is accredited? Does it need to be UCAS or MCerts? They're both UK accreditations. If you have a legal or regulatory objective, I would say yes, your sample does need to. Not all labs test all things to accredited methods. It is not the lab that is accredited, it is the individual test. So really check the lab's accreditations. You may find that they have accreditations for metals, some organics, some TPH, but they don't have it for all. So you're going to take a balance of who's got the best accreditation for the suite that we've identified. Or you might just say, well, actually, we trust this lab. We know they've got good quality systems in place. They have enough accreditations that we're happy with it, and go with that approach. It very much depends on what your site needs. Limits of detection, Fraser's mentioned, but again, you need to check that, because your limits of detection, they're not just a symptom, or they're not just a product of what is the lowest level that the machine can test to. It's also a function of the quality process and the statistics that go on behind the scenes according to the accreditation. So it's not a direct number, but there is absolutely no point in going to site and taking a whole load of samples. And this happens quite often with water. And you find that every single sample you've got it's measuring less than it's measuring a number that is meaningless in comparison to the limit of detection, because your limit of detection is higher than the assessment criteria that you're looking at. So you have absolutely no idea what's between the gap between the assessment criteria and the limit of detection. You can go back to the lab and say, what is the actual direct reading off the machine? But it won't be an accredited number, and they don't like doing it. And it's a bit of a, beg, please. And it's not a direct answer. So just it's very easy to spend a lot of money on meaningless testing if you don't get your limits of detection right. I would also say the same thing happens with units. You can see somebody goes, oh my God, I've got 10,000 watts. 10,000 micrograms is not the same problem as 10,000 milligrams. And if you don't look at your units, and they can change across a testing suite, some labs will test metals to micrograms and then VOCs and organics to milligrams. Sorry, the other way around, soils to milligrams and organics to micrograms. So you have one that's a big number and you think, then you look at the units and you realize it's not a problem. Sometimes you get things reported in percentages. 1% is 10,000 milligrams per kilogram. So if you get something reported in percentages, you've probably got a lot of it. So just bear that in mind. Holding times, which is the time between your sampling and your testing, that was one of the issues when you look at the E. coli testing and bacterial testing, is how long have you got between you taking that sample, packaging it up, putting in your cool box, carrying it from wherever you've sampled it back to the lab. The lab then will book it in, process it, put it into their processing system. That might take some time. How long is that period? Is it 24 hours? Is it 3 days? Is it 10 days? Is it 15 days? How long is it before that sample becomes unviable? because you need to know that for your logistics as to, do I send samples off on a daily basis? Do I send them off on a weekly basis? Because without that, you can end up with the deviating samples, and I'll talk about that in a little bit. And there are other elements that will come into selecting your laboratory. You know, how much does it cost? How do they move the samples around? What's their customer service like? All of these sorts of things come into a relationship with the lab as to which one you use. And my little sort of pictures at the bottom is, are you comparing apples with apples? Are you comparing the same sort of apples with the same sort of apples? Really important that once you have selected your lab, that you stick with that lab for the duration of the project. I think your example, Fraser, was perfect in showing that if you use 3 different labs, you get 3 different results. It's the same soil, it's the same water, but you potentially are going to get different results because they use different methods, even though they both look like they're testing apples. It might be a different sort. So where do the labs vary? What's the difference between them? You've seen the typical sample containers, so the size, the volume of the sample, the container it goes into. Preservatives. We try and avoid preservatives because then potentially we're handling chemicals. However, in some of the British standards, there is a requirement to stabilize VOC samples using methanol. And it has been proven that there are orders of magnitude different between samples that are preserved and samples that aren't. So that's talking about the degradation of organics between sampling and getting it to the lab. If you don't know that, or if you're not compliant with the British standard, then you can have a very big difference. Again, Fraser's mentioned, we take a lump sample. It goes in a pot of some sort. The lab sorts it all out, dries it out for metals. If it's organics, it's going to leave it as a wet sample, but it's going to take a minuscule amount of that sample. If we don't give them a representative sample to start with, how the heck are they going to give us a representative answer? It's not going to happen. So if you give them they're going to take a random bit from a random sample. You need to make sure that you're at least sort of getting the right sort of sample. Oh, we're all shutting down around us. So if your sample is not representative, and I think Fraser gave some really good pictures showing that, it's totally immaterial if your limit of detection or your methodology or your lab accuracy is wrong, because if you've given them the wrong sample to test, you're going to get the wrong answer. But there are limitations. The labs aren't mind readers. They will try and interpret what you're asking them for, but they don't know what you're asking for. They are simply processing your samples, putting it through a test process and coming out with a number for you. But there are certain things they need you to do in order for that to happen. So if you suspect asbestos, they won't be able to handle it because of the risk to the people doing the testing. You need to identify, if you've got lumps of asbestos around, it needs to be double bagged, it needs to be flagged that it's asbestos. Some labs will then turn around and say, we cannot put that sample through the rest of our testing regime because it will compromise those machines and means we have to stop, clean them up, and they can't be used for any more sampling until we've done that process. Or we're going to expose our technicians to asbestos that we can't do. So free product. If you get free product, then they'll have to dilute the sample in order to bring it down to the limits that they can put it through the instrument. And that affects the limits of detection that they can reach for that sample. Pathogenic testing, occasionally we have to do that where we think we might have been an animal burial pit or something like that. Until fairly recently, Porton Down was the only place that could do that, but I now know there's a couple of other labs who can now do that sort of testing. But again, sampling for that is complicated. You need to be suited, booted, and protected. The samples need to be really robustly packaged and sent off. Some couriers won't touch them, even if you're testing as a precaution rather than a known fact. So you need to plan that ahead. The logistics are really important. Microbial testing, only certain labs will do it. So hence, pick the lab that's closest, that's nearest, that's going to allow you that 24-hour window. We have sites that are called red sites. They're the most contaminated sites, the ones where the risks are the highest. Quite often, if you are on a red site, you're going to have a lot more controls and protection in for your drillers and your samplers. You're going to be having people in white suits and respirators. You're going to have decom units and things like that, which I would say are not normal, but are not unusual. But those labs dealing with the red samples from red sites need to have special precautions in place for handling those samples. And if you don't tell them, then you're putting their technicians at risk. And just be aware how long samples. Quite often you'll have a client that says, "I need these results tomorrow." Yes, you can pay money and speed them up through the process, but you can't speed them up quicker than the test takes. So if you want leachability testing, you're going to need 48 hours to put it through the sample processing. Doesn't matter what you pay them, they can't physically do it any quicker. So just be aware that if you don't overpromise to clients, oh yes, we can rapidly do that test, we'll do it within 24 hours. Some of them they just cannot do. It's knowing what the limitations are. Again, Fraser's covered some of this. I've talked about the preservations, but basically if your sample is wrong, if there's not enough of it, if you've got the wrong container, and if it's not preserved, then potentially you are going to get deviating on your results. Does that mean that you can then pass it on to your client? Can you pass them on a deviating result? Is it fit for purpose? I throw that out there. We're seeing more and more labs providing deviating results due to their QA/QC procedures and the statistics that go behind that. And it's an interesting argument with the labs as to who pays for the sample and whatnot, because they say they followed their procedures and you say, well, I haven't got any data that I can use. I haven't yet found the solution to that one. It's a work in progress. Have you found any of that, Fraser, where you've got samples deviating because of QA/QC procedures?
Yeah.
Yeah. Yeah. You do your bit and then they don't quite do their bit, but they follow their procedures, and therefore there's a middle ground where nobody's claiming responsibility. Yeah. So why do deviations happen? Exceeding holding times is very popular. The wrong container is another one. That's another high up there on the list. But I think A and B should be avoidable. If you're planning the works and the lab is understanding of what your aims are, that should be controllable. The QA failures in the lab are less so. The discussions I've been having recently is partly they say, oh, your sample's not suitable for testing. Hang on, you've tested it for all the rest of the suite. How come this bit's not all right? And quite often it's to do with the statistics behind the limit of detection. If they have something that looks outside the norm, they are required to retest it. And they can only retest it if they have got a sample. So if it's VOCs, if you've only got one vial, they've opened the vial, they've done the test, it statistically doesn't match the rest of the testing, they have to retest it, and they've got no sample because it's been opened, so now it's dead in terms of testing time. So they have nothing to retest, so the results are deviating. Also, you can get the scenario whereby this sample is not well, they say not suitable. What is not suitable? I don't know. But they may also decide that it's outside of the statistic limits. They've got to retest it. They put it in the queue for the instrument, and while it's sitting in the queue to go back through the instrument, the sample exceeds its holding time. And you went, well, we've only got that much capacity in the lab to put everything through. And you think, well, why didn't ours get in front? But of course, if ours gets to the front, then somebody else's deviates. So the labs need to have enough capacity to be able to do these things. And I think it's a lack of capacity when labs are really busy that these deviations can occur. I don't know what the answer to that is, but I do think that labs are dealing with more and more strict UCAS accreditation requirements, and they're being audited on it a lot more. So we'll see how this comes. I have asked one of the labs to write a paper on this for the AGS to publish in their newsletter to give people a heads up that it might well be happening. But certainly if you're taking VOCs and they are a critical contaminant of concern, take a duplicate vial. Because then if the labs need, if they come to deviate samples because of their stats, if they've got that extra sample, they can immediately retest that rather than have to go through the process of, we can't test it anymore. So when you ask for your testing, what are you actually asking for? What does TPH mean to you guys? Total petroleum hydrocarbons. Yeah, that's the answer that's going to come back, isn't it? But what does that mean? So for waste classification, you'll want total TPH. You'll want the carbon band C6 to C40. If you're doing human health risk assessment, you'll want the speciated aliphatics and aromatics broken down, and you will only cover C6 to C36. They may well be the same test on the instrument. And it may be that you can go back to you can ask, you get your TPH CWG, you can go back to the lab and say, can you just extend that to C40 for me and give me the rest of the chromatogram? That's doable. But if you need to be aware of what the TPH test is for and how they've tested it. One way around that is a recent innovation by Hazardous Waste Online, HWOL. And they have come up with an acronym system, which I've shown on the right-hand side here on the screen. So if you, and I think they've got about 12 labs now signed up to this. So if you find after your sample, there's a whole load of letters. So say after your VOCs, you've got HS, that means that it's been a headspace analysis. And then CU relates to its cleanup. Has it gone through a silica gel or a fluorosil screen, which takes out, if you like, the natural organic, the humics, leaving the petroleum hydrocarbons behind? Otherwise, if you tested a peat just for TPH on an acid extraction, you're going to get a huge number. That doesn't mean to say it's hugely contaminated. It means you've extracted the wrong thing, or you've extracted everything and it's not all of the contaminant of concern. You need to know what you're asking for. But this way, there is no way of knowing the difference between the testing done between the different labs. They each have their own methodologies. This is one way of addressing that for TPH. You can actually see how they've tested it and how they've reported it. And you can see what sort of chromatogram you're going to get, whether you're going to get the standard sort of graphed, which looks a bit like a stegosaurus kind of graph. And you can look for the various peaks on it that relate to the different contaminants. Or you get something that's a weird and wonderful splodges on a page, which is the new 2D chromatogram, which is, well, I don't know how to interpret them. I have to go back to the lab. So that's our hydrocarbons. Cyanide, you're looking at free, total, complex. Which version have you got? What does it mean? You might be looking at chromium 3, chromium 6. Are they, what's real? Have you got lots of chromium 3? And or have you got lots of chromium 6? Is it real? Could they actually exist the way it's been reported? Ammonium, ammonia, ammoniacal nitrogen, a nightmare. Speak to a chemist. It's really sort of, you need to nail those things when you're actually specifying your testing. Is your sulfate for human health risk assessment? Or is it for geotechnical purposes? Is it for assessing concrete attack? They're not the same test. So if you even have a test that just says sulfates, make sure you're looking at the right numbers for the right thing. Does what you have scheduled give you the data that you require to do your risk assessment or the works that you need to do? That's your responsibility as the person doing the scheduling. So the lab will only test the samples that you give them. You give them a rubbish sample, you're going to get a rubbish result. And it will only do the testing you ask for. So if you ask them to do a certain test, that's what they will do. They're not going to go, oh, I don't think that sample looks like it needs testing for that. It's a bit blue in colour. We'll test it for cyanide as well. They are not going to do that thinking. That needs to be done at the sampling stage. And then you need to include that in your spec and your LODs and what you ask the lab to do. And if your testing is UCAS accredited, the lab is bound to follow process and there is no wriggle room. If their time periods deviate, if their statistics deviate, you're going to get a deviating result. So I'm going to hand now over to Chris with an introduction from Charles. Thank you.
Thank you very much, Jo. Lovely. So we will now pivot from Geo-Environmental to the Geotechnical, and from a consultant's perspective to a laboratory perspective. So our next speaker is Chris. He studied geology at Royal Holloway, and upon graduating, he was a research officer at the University of Surrey. Chris started his career at Surrey Geotechnical Consultants, where he learned his art over 16 years, studying for an MSc Geotechnical Engineering at Surrey and rising to director. During that time, he also served as a guest lecturer at the University of Surrey. Since 2007, Chris has run his own company, RGI, one of the sponsors of this series, where he's provided advanced soil and rock testing, supporting both onshore and offshore geotechnical communities. And we're very happy to have him speak now. Cheers.
Your battery is running low.
You've got half
Perfect
an hour.
timing. Oh, I'll whiz through it. Right. Do I just close that? Oh, perfect. Right. So, okay. Hello, everybody. I had a lot of trouble actually picking a site photograph here. I was hoping that it would be very muddy, very horrible, as my imagination is that that's what sites usually are, and with drilling rigs everywhere and lots of pipes and everything like that. So in the end, I decided to be rather neutral, because when most of these tube samples or samples turn up at the laboratory, they're certainly not clean, and they don't look like they've come from somewhere like that. They look rather messy and horrible. So yes, and bear this in mind that from the site, from boreholes, whatever, these samples then end up in something that is about as clean as a hospital. So it goes from the field into a very nice sort of laboratory where everybody wears white coats most of the time, and we look after the samples and nurture them. But they've got already a huge history to them. Okay, so let's just go back to the basics. The very first lecture was the concept of the geotechnical triangle, of which laboratory testing is an extremely small part. And what's been spoken about tonight, they are all different facets, and there's hundreds more facets in order to put together and satisfy the geotechnical triangle for design. Chapter 49, obviously you may wish to read it. It was very difficult to write because I could write volumes on laboratory testing. And I could actually stand here talking to you about laboratory testing for probably a few weeks, and I'm sure many people have other things to do. So I've actually had to restrict myself back and basically go for the sampling, because it's something that's quite close to my heart, especially nowadays, because of what we see, what we receive, and it's something that would be a good idea to place in your minds. And it's basically those pictures of some of what you are going to see. Bear in mind, people that take samples, drillers, wonderful people, highly professional, and there are some superb drillers out there. But when we receive samples in the laboratory, certainly that are in tubes or something else, we cannot see. And when that was removed from the ground, nobody knew what was in that tube. it could have been anything. We have great hopes for it, and the first people to possibly see it, first humans to see it, since it was laid down, is the people in the laboratory. So it's quite an interesting insight that I'm going to hopefully give you. So, yes, unexpected material in many forms, both through nature and geology and in human input. So what is in the tube, basically? We're asked to test it. Okay, this is what we thoroughly enjoy. Right, let's go for it. This is basically in its most simplest form nowadays. Obviously, we take bulk samples, bag samples, things like that for various index tests. But the moment that we want to test something that's undisturbed, usually for effective stress, it might be odometers, it could be shear boxes, but a reasonably undisturbed sample. On the right, you will see, well, it's actually two aluminium tubes, I assure you, but you will see that at the top of them, there are two different thread types. The right-hand one is the original UT100, which has a huge history, and it used to be in old days called a U4, as in a 4-inch tube sample. But if you look at the one thing that you will note is the very fine thread on it. That is always the giveaway that it is a U100 sample. Even nowadays, we are not allowed to use those as Class A samples for effective stress. They are basically banned. And it's to do with the cutting shoe that is put on the end of the tube. The displacement, the angle of it, it actually fails the ground in front of the tube as it is actually hammered into, like percussion, hammered into the ground. So you can also see that on the top of that tube, the ring is ever so slightly thicker than the tube on the left. The left-hand tube is called the UT100. This was the replacement for the U100, and the identification for you in the field, if you're seeing drillers, is that you can see that it has quite a coarse square thread. Now, it physically is thinner, and that is an aluminium tube, quite clear, well, hopefully quite clearly, but the new test type that came in maybe 10, 12 years ago, is that for Class A, undisturbed samples or suitable for effective stress tests is the UT100. Okay. Now, the problem with the UT100 is it has, because the tube is a lot thinner and because of the coarseness of the thread, it has a severe structural weakness. Now, you can see the tube on the left, that was a UT100, and that is where they usually fail. And it's where the driller, especially if the driller is sampling in stiff or very stiff materials, they have to withdraw the tube out of the ground. And commonly, they will fail if it's an aluminium tube, or at least it's not uncommon, is the best way to put it. Now, they don't like losing samples down holes, and they really don't want to drill another borehole to try and get past that tube. So you can see what people do. They'll actually put a casing down the borehole and squash the top in and try and withdraw the tube. So this is the problem with the new UT tubes, the aluminium ones. Unfortunately, then what happened was some people had a very bright idea that, okay, we won't use aluminium tubes, we'll use steel tubes because they're far stronger. This actually, and very unfortunately, has brought a whole new world to, if I called it undisturbed sampling. In the picture, you can see that these mild steel tubes quite clearly corrode and rust on contact with water. So okay, drillers are supposed to use brand new tubes, but this is basically what happens to the tube. Depending on the environment it's stored or used, it will corrode. The tube will actually rust in contact with the sample itself. That causes huge problems. The pore fluid of the sample will become altered. One thing that is a very common belief now, and I certainly have it, is that the pore fluid chemistry controls or has a huge effect on the measured properties of clays, certainly. Obviously, non-cohesive materials, they don't have that kind of interbond chemical attraction, but clays certainly do. So reducing the pH of the pore fluid really isn't good. This acidic water will definitely change the pore fluid chemistry of clays, which may alter the strength and stiffness. Interestingly, it also has, this rust has a physical effect. If it's actually growing on the inside of the tube, it's compressing the sample. So it's changing the sample fabric as well, which isn't very nice. So if we are being asked to measure stiffness and strength, we have actually just, in theory, over-consolidated whatever the sample is in there. The problem with this as well, the sample physically rusting to or corroding to the inside of the tube, means that we actually can't get it out of the tube. I have broken 3 extruders trying to get samples out of mild steel UT100 tubes. They just lock in, and then we tell the client and have to explain to the client that we've just lost their sample, we can't get it out. But we obviously explain very nicely in the reasons why, and it's just a great shame because that sample has been lost, and they usually cost a reasonable amount of money to get out of the ground. Okay, going back to the UT100, the aluminium one, I've taken a picture of the inside of the tube. It's quite clear aluminium is reasonably self-lubricating. However, it's not totally chemically inert. You have to be careful because it is aluminium, and pore fluid, especially saline pore fluid, will attack aluminium and destroy it and react with it. Okay, so you can see the nice smooth lining, which is what the UT100 was supposed to be. Okay, a different type of sample is that these are thin-walled push samples. Offshore, they're very, very commonly around 70 millimeters, but they can be used onshore 70 millimeters to 100 millimeters diameter. The cutting chute is actually machined directly onto the tube itself, and these tubes can be up to 1 meter length. But out of interest, if you look very carefully, the center tube, you can see a very nice machined surface, cutting surface on it. If you look to the one to the left, you can see that that cutting surface really isn't regular around the tube. It disappears towards the left, and the same actually to the right. It looks more like it's been put, the cutting edge has been put on more likely with an angle grinder or something like that. So if you're trying to take Class A samples, you're really not going to. One of the things that can happen is the tube can then wander off its line because it's not cutting perfectly in a singular direction. So this is one of the things that we have to come across, but this is what we see in the laboratory. Okay, rotary coring, another form of sampling. This actually requires that you have a core tube, commonly called a triple barrel core tube. So you have the outside rotates, holding a central stationary steel liner, which inside that you can put a plastic liner to catch the sample. The outside actually progresses down the hole with the help of drill fluid, removing chippings, etc., or slurried clay in many cases. And you end up with a sample in a casing, a plastic casing that you can pull out. Now, these can provide, and I say can provide, very, very high quality samples, especially in stiff and very stiff clays. The sample on the right is actually an unprepared and untested sample. That is actually what came out of the core barrel. All that's happened to it is that it has had the outer layer taken off it, because when you're using drill fluids, etc., as soon as the cores are taken out of the ground, they must be opened and all of the drill fluid removed. Otherwise, whatever the material is, it's going to change its moisture content. And if it changes its moisture content, it's going to change its effective stress. And if it changes its effective stress, it's going to change its strength, etc. And if there's fissures in it, they may open up. If it's drying, it'll desiccate and we end up with a very high effective stress. But the long and the short is the sample will change its structure and strength and stiffness, and they can be very difficult to recover. So the sample on the right is something that we would then put in a soil lathe and make it into a perfect cylinder and then test it. Okay, now, seems to be a slide missing. This is basically supposedly the best of the best. It's a hand dug block sample, and as you can see, it's in the box. We can't see in the box. It's the famous game, What's in the Box? And they generally aren't taken from great depth, but they are supposedly the most undisturbed sample that it is possible to take, because they have been physically hand cut out of the ground, the box built, put over the top, it moisture sealed, filled with foam, and then they cut underneath the block, very carefully turn it on its side and put a bottom on it. So here we are, a very large box. We were asked for this material that when we got it open, we then had to cut the block that was inside and take 200 by 100 millimeter triaxial samples out of this and prepare them for very specialist testing. We opened the box. That was what was in the box. You can see the scale at the bottom, 200 millimeters. We were supposed to take vertically 200 millimeter length samples from that. You can see the structure of this block. It is not really suitable, certainly vertically, for any kind of triaxial sample. The idea was that we should cut a piece out, put it in a soil lathe and trim it down to a perfect cylinder. You can see by the structure of this material that really wasn't possible. The problem is it cost a lot of money to get that block, and in fact there were two of them, out of the ground. The shame was that they were then put on the back of a lorry and came a few hundred miles on the hard suspension of a lorry. And so if the fissures and fractures in this block weren't opened up, they certainly were by the time we received it. So feedback from the field, somebody digging and trying to prepare this, really it would have been nice if they'd known what was required of the block, because in them hand digging it, they would have seen that it wasn't possible. However, they could get very good field evidence of the material itself. It was possible to possibly produce some smaller samples for index testing, but certainly nothing too good. I think I have got a slide missing. Okay, back to the UT 100s. As they are pushed into the soil, and this is, you can see that this is actually a fissured material. This is a tested sample, and if you look, when we split samples, we always cut up to halfway through and then peel the sample actually open the rest of the way. So on the right here, you can see where we've actually pushed a blade into the sample and then peeled it open. So you get two types of pattern in the material. One tends to give away that it's a clay on the right hand side, and then you can see the actual features of the material itself. What this actual slide is about is disturbance. And if you look where the two halves of the sample meet, you can see the drawdown of the fabric in this particular sample where the tube has been pushed in. It has actually disturbed the outside edges of the actual sample itself. This can't be recovered. It's actually damage to the sample. So disturbed or undisturbed, it certainly isn't. Slightly disturbed, it is. We could argue forever about exactly how disturbed it is, but it is definitely a disturbed sample. Now, from what I just said, I would say looks like quite a disturbed sample, really. This is the next level of really disturbed sample. As you can see, towards the boundary, this material is actually like upside down saucers. It is completely distorted at the outer edges, and anything that was actually horizontal in it, which is towards the center, has actually been bowed down rather a lot. The interesting thing about this is that I've been talking about UT 100s rather a lot. So we might expect that this is just a UT 100. I can tell you that it isn't. This is a rotary cord sample. It's supposed to be a very, very high quality sample. But clearly what has happened here is that they weren't actually rotary coring. They were actually, unfortunately, without knowledge, basically just pushing the core barrel down into the sample, and it has basically completely destroyed this material. So getting good parameters for design out of this material, I would say, no, you're not. It's not going to happen. If you were looking for quite a high-end test, a local strain test, you really would be wasting your time. These are tests that we would restrict. These are materials that we would have to restrict. And in fact, particularly with this one, we caught on to the fact that it was highly disturbed, and the client asked us to do a very, very bottom end test on it, because they just said, can we get anything, and what's the minimum that we can get? So we refused to do anything advanced because we don't, it was absolutely pointless. This sample parameters on this are absolutely poor. Now, just quickly, we have a perfect sample, and you can see that there is near as possible no actual disturbance on the outer edges of this sample. This is actually a tested sample. You can see that it failed in shear, and you can see the nice shear plane running at an angle straight through it. This is actually an extremely soft, highly organic clayey silt, very soft, and it has been taken with a thin-walled aluminium push sample. Okay, so it's the ones that I was showing you, that there are 3 of them. Not a UT 100. So we can get perfect samples, and we do get a lot of perfect samples in the work that we do, but it's important to show you the damage, the structure of what does happen and what does turn up at laboratories. And we have to deal with this, but we have to report this we do report it to the client. I mean, very often with some of the other pictures, I'll be trying to restrict the samples with them. Yes, I have got a slide missing. It's a shame. Let me just come back. What I was going to show you was in the UT 100. There's a slide after that that showed you the mild steel version, and the picture down that, and then there's a picture down a mild steel version, and you can see the corrosion and the fact that the soil is totally caked and smeared inside this tube. That's actually, I have to say, a real shame, because that was one of the crucial parts of this talk, that the UT 100 is not a Class A sampler in the slightest. The question was going to be, or the simple question I was going to ask you is do you think the sample's disturbed? It's very clear that it is. So, from site to the laboratory, looking after the samples as they are taken from the ground. Rotary core samples would have to be immediately removed from their mylar tubes, the drilling fluid taken off them, and preferably they should then be mildly shaved, say 2 to 4 millimeters off the complete diameter of the sample to remove any influence of drill fluid. They can then be moisture sealed very carefully, but all of that is in the chapter 49. The actual instructions and depth of it is there, so I don't really need to go on too much about it. Samples should be kept away from direct sunlight. It will heat one side of the tube and not the other. Therefore, you will get swelling in one side of the sample and not the other, and it will be changing its fabric inside the tube. Especially overseas in very hot countries, or it really does change it badly. But even in the UK, and obviously climate change, etc., we have to be very careful. The samples have to be protected from loss of moisture, because we go back to moisture content, effective stress, etc. It can be altered. The samples must be protected from being vibrated or banged, knocked, all of these things. They are very fragile. In an ideal world, they should be stored upright. UT tubes, okay, but certainly others should really be just stored upright. When these samples arrive at the laboratory, they should be kept at a stable temperature so that they don't cycle. No more than 5 degrees. It would always be nicer to be better than that, but it's the allowance for laboratories and how they store. I don't know them all. I store mine, they're within 2 degrees variance, and they are permanently kept at that. And one of the most interesting things, or one of the little sidelines, I will call it, if a tube sample is labelled that there are some index tests on it and that there is also an effective stress test, please tell the laboratory the effective stress test comes out of the tube first. It's the one that is totally dependent on moisture content, and also people tend to try and push samples out of tubes and take rather a lot out of the tube, so they don't leave you any choice of the sample that you're going to use for the effective stress test. So always take the highest level test first, and then everything else that can be used for index tests. Although testing is a process and it should be repeatable, we have to remember that every sample is unique. Even if they were taken within centimetres of each other, They are unique. So you will possibly get some variance in them. It is perfectly okay to have that. So I've heard people say, oh, we all know the values for London clay. Well, my answer is I don't. That's why I test them, because they are different. You can average things out a little bit and have a ballpark, but they're never the same. Please beware of that. Okay, testing is carried out in a way to preserve the in situ parameters for measurement, or at least as part of the test, to return the sample in the most sympathetic and controlled way to its exact in situ characteristics. This is for the best possible parameter determination. If we were talking about a routine effective stress, isotropically consolidated, undrained or drained, the isotropic consolidation is really the one that's trying to get it somewhere near its in situ. But then we start moving into the higher end testing, anisotropic consolidations. Those are tests where we take the sample through part of its stress history, because the samples have a memory. And if we take it through part of its stress history and we approach its in situ stress point from the right direction, we will then be, and rest it there so that it's in equilibrium, we will then be gaining the best parameters that we can get, and hopefully removed a little bit of the disturbance, but we can certainly improve the sample. We may not be able to turn it into exactly what was in situ, but we'll get it to the best state that we possibly can. Okay, in conclusion, we need a ground model for professional design, and for this the engineer needs to carefully design the ground investigation. This is the problem, because the ground investigation being designed means that you already need to know what laboratory testing you need, because you need to know the parameters that are required for the design. Now, the problem with that is if you know that, that tells you what type of drilling and sampling you need. However, that's usually decided a little bit later down the line. You actually need to know quite from the start the samples that you're going to need to take, possibly the number of them. But I fully understand this revolves around money, and we all do the best that we can. But it's the sample quality of what you need. If you're using finite elements analysis to design something, you really do need good parameters, because it's relying on those, and that is what the very high end triaxial effective stress tests can produce. But you need to have a very good sample to give you that really good number, so that the finite element analysis can be done, so that a very nice design can be carried out, everybody's happy, and everybody's saved a lot of money. So it's this weird circle of, at what point do you decide and know what you've got to do? I'm sure lots of people have plans and companies have plans and lots of people get together, but it's something that's fundamental. Unexpected ground conditions can feed back into the system for foundation design or further explanation. We've come across very unexpected things and parameters in materials, I can assure you, but it's the honesty and the integrity that we are telling the client there's something not right. If we find something with a sample that isn't doing something that's expected, the first thing that we do is calibrate everything and check. If something appears to be not so stiff or doesn't have the strength that we would expect, we will be, it's definitely a hands up thing. But the one thing that I will tell you is the history of the test, the behavior of the sample is in the results. The initial description is a description in the laboratory with a prepared sample sat on a table. The test that follows shows the behavior of the true material and what it then yields in its test parameters. The sample is then removed and we photograph it in how it failed, and we split the sample to show its texture. If you ever have something that you look at and you're scratching your head a little bit, the most important thing to you is the initial description. You may not quite understand what happened went on in the test. You can look further at that later, but it's the split sample photograph shows you basically what it was that tested. Many years ago, and I am talking many years ago now, we were testing a complete borehole, and right in the middle of a series of brown clays, there was a grey one. And it was because that sample, and it came out with totally different parameters, I'll use that word. And as it turns out, that sample didn't belong to that borehole. We'd got a relabeled sample. It just didn't belong. And okay, that's in history. It doesn't happen nowadays, I'm certain, I hope. Okay, so good ground investigations can save a great deal of money in foundation design. Okay, there's levels that we can approach. There's levels that are required. There are levels that everybody wants to achieve. And I think it's the passion of you all as geotechnical engineers to try and strive for the best always. The best is not always possible, but it is to go home and have your hand on your heart and say, I did the very best. And hopefully for somebody else to agree with you about that, because that is where your confidence can come back from. Okay, information, planning, knowledge and communication with stakeholders at all levels is key. I find commonly now that clients from the top of the tree, for want of a better description, they will talk to me before anything starts, because I can talk them through the parameters that they can get, what they would need to sample, how they would need to sample it, and that goes in their mix, and they can put something together. And they then have expectations. The very nice thing is the laboratory has expectations, the site engineers have, and it's very nice that everybody is brought in. So all stakeholders, it's being brought on board. It's ownership. If you can give everybody ownership, they'll pull together and pull very well. So engineering is driven by experience, learning, passion, and getting your hands dirty. Engineering, yes, I appreciate everybody works in offices, but go and get your hands dirty, because you've got to touch it, see it, feel it. You can see where it is. You can see what it is in relation to, and you can not only feel it, touch it. When I was very young, you used to be able to put bits in your mouth, but you're not allowed to now. And especially in the light of the previous two lectures, I really wouldn't want to put anything in my mouth now. But that's how you used to test for silt, which we're not allowed to do. In fact, just quickly, the test for silt, wet your hands a little bit, rub clay, and if it goes white within 30 seconds, you've either got a pure silt or it's a very silty clay. If it retains its colour, it's clay. So, okay. Thank you for your time. Okay, I put this there because it's just the tease. It's the big circle. It's what do you do first? What do you control? What do you need to control? So which does come first, the horse or the cart? Thank you.
Cool. We will now have a very brief question Q&A until we're kicked out, or for sort of 5-10 minutes. Yeah, I think the only caveat is in environmental, you get your nitrile gloves dirty, not your hands.
Yes, exactly.
Cool. Do you want to sit for some very brief questions? We have microphones if anybody in the room has questions. I've taken down a couple from online.
Yeah.
I've written them down. Are there any questions in the room? Cool. And if you can be, they are quite directional, but cool. So I think I'll start with there was a question around where you have multiple labs testing the same material and getting different results. Which lab do you take?
That is a golden question. There would be no way to know really without knowing what they've done to it. You have to really go into details and review those methodologies. But it's like with sort of used to do topo surveys. Never survey the same point twice because you just never know which one to choose once you've done that.
I would say you would probably end up having to take the max value unless you've got to be conservative. If you don't have anything to justify why not.
Unless you've used 6 labs and can do stats on it.
Potentially, but yeah.
You'd have to be confident you're testing your apples against apples and all that lot. But yeah.
Okay.
Aha.
The answer is don't spend your money 3 times.
That's pretty good.
If you do, you'd be prepared to scratch your head for a while and try and work out what that means.
Yeah.
Um,